Okay, welcome back. Today we're going to be doing the Routh stability criterion and the Routh array. We're going to be doing an example, but just to get a background of what the Routh stability criterion is, it's a mathematical technique used to describe or determine stability of a linear system. And this is going to allow us to explicitly compute the roots of the characteristic equation, depending on the system's, if the system is an open loop, closed loop, and whatnot. But the reason why we do this is computing the roots of the high polynomial is quite difficult. We're able to determine stability without explicitly solving for any roots. And the way that we're going to be doing this is know how many roots are in the left plane or in the right plane, or possibly in the imaginary axis. And this is because we want to know if our system is ultimately stable after we've modeled it. This is useful when we're modeling, understanding if it's stable, its natural state, without any control. After we understand if it's stable, we're then going to see if it's even controllable. But that's for a different technique or in a different process. But just to get the general idea of our process, this is what we're going to be doing. But to start, let's have this polynomial here, this characteristic equation. We're going to start with S3, 3ks. Okay. And the thing we want to do is, in this case, we're going to want to find the desired range. Oops, that's crazy. Of K. Okay. So that the system is stable. Okay, so we've determined what we need out of this problem, and we're going to first set up our tabulation. So for the tabulation, we're going to start with the highest, which is S3. And we're going to pull the coefficients out. So for S3, or S to the third, this is 1. And then we proceed with the next following, skipping 2. This one, the coefficient for that is k plus 2. And I'm going to put it in parentheses. Okay. So then we proceed again with the second. We notice that it is 3k. Okay. We don't have any more s's, but we do have 4, and that's going to be our 0. So we'll include the 4 there. And ultimately, intuitively, you might think that because, well, we've done S1 before, we can just put k plus 2. But this is not the case for determining this row. What we're going to need to do is actually apply the determinant, or use the determinant, to find the value, in this case, for that row and column. So if we pull and use the determinant, we know that this is going to be 4. Nice. We then expand the determinant, and this is going to be 1. And what we do here is just times this, and as well across here. So let's do that. Okay, and then we times this. Okay, continue down. It's 4. We have 3k squared plus 6k. 4. And we can just put this here within, for the S1 row, into column 1. So this one here is going to be such. It's going to be pretty tight. Cool. And this one's also 0. And then for S0, because this is the last coefficient, we can just end this here at 4, and our tabulation, our array is complete. But that doesn't finish the problem, right? We remember that the problem asked us to find the desired range of k so that the system is stable. Now, in order for us to consider this a system that is stable, the number of signs that switch within the first column determine this. So at any point, if there was a change in the sign, we would know that there would be a pole there, and that would actually consider the system unstable. Okay, and so we're going to be finding this k, and the way we're going to be doing it is actually looking at the column or the array that we just found, and we're going to be doing the quadratic formula to determine the roots for this. So if we do this and pull the roots out, we'll be able to find our values for k. So if we use the quadratic formula and did all the fancy math, we would then find that k is actually, for the positive, I'm not going to use this, k1, and this is for the plus, and if k2 is for the minus, we would find that k2 is equal to -2. Know that k is less than, well, because we did the negative. I'm going to put it right here so no cause confusion. That k is greater than 0.528. And the one that's going to prove or result for a system that is stable, we're going to go for the positive value. And that is because we're not going to get any signs changes within the array itself, right? So this here would be stable, whereas this one here in the bottom would result in a sign change. It would cause oscillations or even diverge and is unstable. So the final answer for stability range would actually be 0.528, but our range would actually be this here. Okay. And that is our problem. Thanks for watching.